Well, the first part of today's lecture is about the background of my research, and before that, I would say that my English is just okay. So if anything is unclear, please stop me and let me try to explain you again or rephrase my expression. So in the past 2 or 3 decades, the sustainability issue has also made the architecture industry to have a transition to like a low energy consumption and also the net zero building. And so we also see some like a turn like a high performance building. But when it comes to the high performing building design, usually the engineering will take most of the design part, and the architects usually will be excluded or not very engaged in the design process of the high performing design. And we can also see that the most widely used approach or the technique is about like a high performing windows and the material, and also using some active technology like the heat pump to reduce the energy consumption of the building. But this is obviously not very close to the architecture design. However, we can see that in the real world, but there are still many real world projects that can be featured as a high performing design. And also you can see the architecture and the architects can play a part of the design process. There have many there still have many examples of this kind of example, like the Frankfurt Commerzbank building and some kinds of the high-rise or the middle-rise building in Singapore, because I stay in Singapore for 1 year, so I'm a little bit more familiar with their context. So it means that the building or the performance can become a driving factor in the architecture design, and in reverse, the architect can still play an important role in the high-performing building design. But even the designer or the architects want to design a high-performing design, but the problem is that how to design that. Mostly, we can see that in this slide, you can see that usually the designer will have some hand drawing or have something drawing using the computer or like a Photoshop to draw some arrows in the building, and to see how the wind will be flow inside the building and how the sun will be reach the building. In general, this principle is right, but it is inaccurate and is not very precise, because you are just based on your empirical or your experience. So in the 90s, the 1990s, and also in the year after the 2000, the technique like the building simulation become more prevalent in the architecture domain, and we can see many designers and researchers start using the top software like the CFD or other kinds of like eCAADe to do the building simulation. However, when we're using the building simulation, the simulation only help us to find the problem but cannot resolve it. So there's still a very challenging task for the architects to try to improve the building performance simply using the building performance simulation. And there are also some research papers state that they usually have a very small number of design modification or iteration when using the simulation, because they are usually very time consuming to change your design and conduct another round of the building simulation. So to solve this problem, in the past 10 years, there is a trend in the computational design and the parametric design become more popular, and especially like the two, like a grasshopper, and also the embedded genetic algorithm like the Galapagos provide the designer a new way to solve the building performance challenge using a more intelligent way. So there the computational design optimization have a three major part: the parametric modeling, which will be define a design space for the optimization algorithm to search for the high performing solution. And the second element is the building simulation, which is actually to evaluate the building performance and let the optimization algorithm to know whether this design is good or bad. And the last component is the evolutionary algorithm, which will conduct the design optimization process, which using technique like meta heuristic to try to search for the high performance design in the design space. So here is the basic workflow of the computational design optimization. So the first thing is in the bottom left. The designer first need to translate their design concept or scheme into a parametric model, and then to connect the parametric model to the performance simulation to evaluate the performance of the design, and then to lastly to connect the simulation to the evolutionary algorithm to let the to establish this feedback loop, and then the evolutionary algorithm will try to change the parameter of the parametric model, and then to get another the performance evaluation feedback from the simulation, and then using this loop and to try to using an iterative process to gradually to find the high performing design. And so compared to the previous one, the designer have to manually to change the design and conduct the design the building performance simulation. This approach is obviously more efficient and statistically more scientific and or more reliable from the numerical point of view. However, the conventional computational design optimization still have its own limitation, because the computational design optimization is a technique mostly adopted in the engineering area, because they are usually focused on the problem solving. But in architecture design, the major issue especially for the early stage architecture design, the problem solving may be not the most important issue, but the problem framing may be the more important than the problem solving. So here, if we're using the conventional computational design optimization in the early stage architecture design, we can find that firstly, in the left-hand side, they have a design brief and also design condition, and then the architect have to conceive a design concept. For example, they think that in this design condition, maybe the courtyard is a good solution, and then they change. They do the parametric modeling and to try to represent the courtyard building into a parametric model, and then connect it to a computational design optimization workflow and run the optimization. Of course, the optimization may provide the designer a high-performing solution with the best or the most efficient form of the courtyard. However, you can see that because the designer only embed the courtyard building into the parametric model, so the optimization result will only provide the information related to the courtyard. But for the early stage architecture design, the best or the most efficient shape of the form of the courtyard may be not the most important problem. The most important problem is that how the architects know whether the courtyard is the correct measure or the correct way to in this design, and how if the courtyard is the correct way, how many courtyard is the feasible or the best number. For example, is 3 small courtyard or 1 large courtyard, which will be better from the performance perspective. And also, if that's possible, to combine the courtyard with other design strategy like the terrace or the steel in the building design, and to make the performance to further improve the performance of the building design. So you can see that if we're using the conventional design optimization approach, the design process, the optimization process is too linear and close, and also very time consuming. But the information provided provided by the organization result is also not very useful for the architects to do the design exploration and ideation. So while we are talking some limitation with the computational design organization, so the another very important thing is how the architects do their design in the early design stage. So there are also some research paper discuss this issue, and here is a sum. And mostly you can see that the architecture design process is like an iterative process that with something like you do some modification of your design and then evaluate your modification and then do another round of modification. And also the middle one set the early stage architecture or the early stage design is like the combination of the divergent exploration and the convergent exploitation. And the image on the right hand side is showing one real world example that how the I would say the experienced architect do their design. You can see that most the paper says that for the experienced architects, they usually compared to the architecture student, they are more capable to conceive more design alternative at the beginning of the design process, and then they can. This is just like a very broad design exploration process. They need to firstly to try to explore different possible design direction and then try to converge to one or two solution and then to do the to further develop the design. So this is not the it's not a very linear process that I conceive one design concept and then I just directly to automate this design concept. So you can see the difference between the computational design organization process and the architecture design process. So if we understand the limitation of the computational design organization, so if we want the computational design organization can assist the architecture design, for me there have two questions to be answered. The first is that whether the computer can independently generate the building design as diverse as architects. And the second one is that possible for the computer to actively explore the different design possibility as the architect does. So these two questions can be also translated into two technical challenges. The first one is the design differentiation in the parametric modeling, and the second one is the design exploration in the computational design organization. So for the first thing, the design differentiation in the parametric modeling. So we can see that if the human designer to conduct the design, you can see there usually the different design alternative will show very significant structural differences. However, if we take a look on the design proposed or used in the research paper, we can see the building usually quite simple and usually do not show those structural differences. And for example, like the one in the left-hand side, even the whole cylinder can be changed or rotated, but it's still just a cylinder. So it means that for the early stage design, if you're using this kind of the parametric model, you're just stuck by the design concept of a cylinder building geometry. So this is very popular or very common to see in the research paper, but this is not the thing that the researchers intend to do, but this is also some inherent limitation in the parametric design. So there is another paper to talk about this. So if we're using the technique like the ladybug, they usually have a very strong logic connection between one component to another component. And then when you expand or try to develop this whole the parametric design network, the logic will become more and more inflexible. And also you can find the design will although the design can be changed a lot, change by the parameter or the variables, but you can see that mostly they will just change in a very subtle way, but not a structural way. So there is also a term called this like a parametric locking. It is like when you develop your own parametric model, you will lock in by the building typology or the geometry represented or the generated by this parametric model. And the second technical challenge is the computational organization. So the basic mechanism of the genetic or the evolutionary algorithm is that they try to using some meta heuristic approach like evolutionary strategy to find the best solution in the design space. And on the left-hand side, you can see that they usually can be, maybe this is not the correct one, but you can still understand the process is that they first will do some random sampling, and then they will select the best one in this set of the random sampling design, and then try to recombine, or we call the crossover of this best design individual, and try to see whether the recombination can produce more better design individual, and then they're using this process to iteratively try to evolve the whole design population. But usually, for the design organization process, like the diagram on the left-hand side, they will usually converge the whole design search into a very specific or small region in the design space. So typically, we are assume that the whole design space have only one optimal solution, and then the objective of the organization is to find this best performing design. However, in the early stage architecture design, we will say that there are usually not a global optimal solution for the design problem. There are usually many or several design alternatives can also have a similar or competitive performance, because you, other than the building performance, you also need to consider some factor like a functionality and aesthetic of the architecture aesthetic. So there have many trade-off design that maybe also all can satisfy the objective of the general objective of the architecture design. So if we have such a design space, there have many possible or the potential high performance or the feasible solution, like the diagram on the right-hand side. It's obvious that we cannot use the conventional evolutionary algorithm to search such a design space, because they usually just converge the search into one region in this design space. But in fact, we want the organization can produce all these high performing solution for the designer, because so that the designer can have the architects have more freedoms in the when they choose one of these design or try to combine the strategy or the implications shown in this design. So this is important for the organization algorithm to identify as many as possible high performing solution in the design space, rather than just focus on one of them. So let's come back to this the conventional design organization process. We can find that because the designer have to first propose a design concept, so we can see that the design organization process can there still have a strong tendency in the design fixation in the result of the organization, because they cannot provide anything other than any other information other than the design strategy embedded by the architects. And the second one is that we can see that they have a strong the causality relationship between the input and the output, because the architect input the courtyard building, so the output of the organization is also a courtyard building. So in other world, you can see there is a term in the artificial intelligence called garbage in, garbage out. It means that you just input some useless thing to the computer, you cannot expect the computer can get you to output some useful information for you. So in order to address this challenge, or to say the purpose of my PhD research or the development of the EvoMass is to address the limitation as mentioned above. So so in this part, I will to present how the EvoMass to overcome the limitation in the conventional parametric design and the optimization algorithm. So the whole thing is that firstly I will to introduce the purpose of the EvoMass and give you a general or the brief idea of what is EvoMass and how EvoMass can be integrated in the architecture design process. And the second and the third is to talk about the mechanism of the design generation and the design optimization. And then we will show you some very simple example to see how the EvoMass can be integrated in the architecture design process. So there are several features can describe the EvoMass. The first one is the integrated and coding-free building machine design generation and optimization tool, because the programming is still quite challenging for most of the designers when they use the parametric design and the computational design optimization. So when the designer using EvoMass, they don't need to do the programming. They just connect some component in the grasshopper, and then they can start to run the optimization. And the second one is that the EvoMass have a great reusability and capable of applying to various building machine design tasks. It means that you can use EvoMass in many design scenario rather than just some kinds of the building like the high-rise building. So so when you know how to use EvoMass, you can apply it to different types of the design tasks and to repeat the design optimization process and get the result. So it means that once you establish your own optimization workflow, you can use this workflow next time in the next design project. And the third one is that the EvoMass can provide designer with optimization result with higher design diversity. And the purpose is that to help the designer to extract the information from the optimization result. So this comes to the fourth feature is that the aim of the development of EvoMass is to help the designer to do the design exploration and information extraction rather than just provide the designer with a direct design solution. And then lastly is that because I have already observed that when the designer using the EvoMass, they usually do not just run the optimization one time. They usually will be repeat the optimization process and try to reframe and change their design problem and or change their problem framing and gradually to search for a satisfied or desirable solution, or this solution is not a direct solution, but more like the starting point for the design development. So this is more like a human-machine co-evolutionary design process. So here is the basic design process using the EvoMass. So this is on the left-hand side, you can see that the input is still the design brief and the condition, but for the architect, they do not need to conceive any specific design strategy like the courtyard thing. So they just define the constraint and the objective, like I want to maximize the daylighting, or I try to maximize the potential in the passive heating or passive cooling. And then they are okay to run the optimization process, and then they get the result and to try to extract the information from the result. And after the information extraction, they can redefine their constraint and objective or try to reformulate the design problem. And of course, they're okay to see that, okay, this is enough for my design exploration, and now I can start to further develop the design concept based on the design information provided by the EvoMass. So here comes to the brief idea about the design generation. So before we talk about the basic mechanism of the design of the EvoMass in terms of the design generation, we I first analyzed why the previous or the conventional parametric design is not suitable for the early stage architecture design. So we can see that there have two types of the parametric model, which I saw in many research papers. The first one is the very simple one. That usually they are just represent one specific type of the design strategy, like the courtyard, the steel, or the solar envelope. So you can see that this is like when you're using this type of the parametric model, the parametric model is actually just define a design space. Design space represent this type of the building. Or for some other researcher, I see they can combine different parametric model into a combinatory one, and then to using this model to generate different types of the building. But this is also problematic because each of the design generated by this combinatory parametric model is still only one specific solution from one of these design spaces. They cannot combine the design strategy or the feature from different design spaces. For example, you still generate the building with a courtyard and a steel, but you cannot combine. You cannot get a design that simultaneously with a courtyard and a steel. So this is the problem of this kind of the parametric model. So if we are using this kind of the parametric model, the design space is just like the on the right hand side. You can see if this light gray line is the design space for all possible design solution. Each of these parametric model only cover a very small portion of the whole design process. So they have two problems. The first problem is that in some cases there is no satisfying or optimal solution in the design space. It means that you are using the wrong design strategy for the parametric modeling. Or in some cases, there maybe have one or two high performing solution in the design space, in the design this small region, but you still cannot to find all the possible design alternative from the optimization process, because the optimization can only identify this one or this one in this region and cannot find the other one outside the region. So if we want to resolve this problem, we need to establish or define a design space. We need to combine these small design spaces and try to make up a very large one. And so that for this large design space, you can see that they can cover many potential high-performing solution. And then for the optimization process, they can try to identify this solution for the designer. So it can also to increase the design diversity in the optimization result. So to achieve this purpose, in the EvoMass, I using two principles called the additive and the subtractive from generation principle as the basis for the parametric modeling. These two principles is very simple and easy to understand. And the most important thing is that you can use these two principles to describe or interpret most of the building form in the world. So you can see basically every building form you can using these two principles to describe. And another very important factor is that these two principles also have a very tight connection to many passive design strategy like the courtyard, the sky garden, or the cell shading, or the solar envelope. So it means that if we can use, so if using these two principles, we not only can find a very we can to define a design space with very high design diversity, and we can also to find the design in the optimization result can also reflect very rich information for the passive design strategy. So this can also help. It's also easier for the designer to understand the architecture implication in the optimization result. So for these two algorithms, the geometry operation is very simple, just using the Boolean difference and the Boolean union. Another important operators in these two algorithms is the alignment. If we just using the Boolean difference or the Boolean union to generate building from there, usually you can create many different types of the chaotic design. The most commonly seen one is like this one. They usually have a very too small void in the building volume, or very too small void in the inside one predefined design boundary. But this so they will create a very small gap between these two elements. And this small gap is usually not very useful from the architecture perspective. So in the EvoMass, the algorithm will detect this kind of the situation, and then to conduct the alignment to merge this small void or the small box to one large one. So it means that they can eliminate the infeasibility in the generative design, and on the other hand, they can also increase the design diversity in the design space, because it means that if you define like a free small box or the small void in the building meshing, you can see that they can actually generate one large void if they are all very close to each other, or one large void or one small void if two of them are very close to each other and one is separate from them. And also another the third situation is that the free small void. So in that case, we can use one logic to generate very diverse design solution for the design optimization to search for. So if we come back to this diagram, you can see that the simple parametric model and the combinatorial parametric model, the design space is either separated or just explicitly bounded, but not but still very confined. So, but for the design space divided by the subtractive and the additive algorithm, because the two algorithms do not represent any specific design strategy, it means that all this design strategy is implicitly merged and integrated in this design space. So the strategy is actually need the designer to extract it or to try to understand it from the optimization result, rather than just to see just to embed it in the parametric model. So here is the way that we can establish or define a very large and unified design space for the for the design optimization process. So another issue for another limitation for the conventional computational design optimization is the evolutionary algorithm. As I said, that they will usually converge the whole design search process into a very small region in the whole design space. So in the EvoMass, I developed a hybrid evolutionary algorithm called the steady-state island model evolutionary algorithm, which using the island model to separate the design population into several subpopulations, and then to guide each of the subpopulation to try to focus on different regions in the design space. So in that case, it means that the result, the optimization result can be can contain the high performing solution from each of these regions. So it means that if you still remember the diagram have a different high performing solution in the whole design space, you can see that using this way, the SSIEA algorithm can extract more than one high performing solution, and then they can provide multiple design alternative for the designer to understand the design problem. And this is especially important for the subtractive and the additive algorithm, the generative model, because for these two models, they are usually can generate several competitive or several high performing solution for the design problem. So in that case, it is more important for the evolutionary algorithm to extract this high-performing solution rather than just focus on one of them. Because if we are still using the conventional evolutionary algorithm, we will lose the diversity in the design, in the result of the optimization, and then they will be significantly undermine the potential of using the subtractive and the additive algorithm for the design generation and optimization. So we are very close to the end of this first section. So we will present you three very simple examples when I develop the EvoMass to try to present the basic logic of using the EvoMass. The first example is we try to optimize the solar energy potential for building design for this orange design on the screen. And the design is based on Nanjing, where I live, and also I consider two performance factors. The first one is the summer solar irradiation, and the other one is the winter solar radiation. And we're using a single objective optimization to combine these two objects. Because firstly, I think the multi-objective one is a little bit usually is misused in architecture design for many cases. I will discuss this issue tomorrow. And the second one is that using the single objective usually can improve the search efficiency for the optimization algorithm. And the meaning of these two factors, we're using the summer solar radiation to subtract the winter one, is that, and the optimization objective is try to minimize the differences between these two values, because if the differences is very small, it means at least either the summer solar radiation is very low or the winter solar radiation is very high, or both. So if we try to minimize these two values, the difference between these two values, it means that we can achieve either a very good passive cooling in the summer or very good passive heating in the winter. So when we're using this objective for the optimization and then to run the optimization using the EvoMass and get the result like this one, you can see that because we're using the SSIEA, so they can produce multiple solutions rather than only one optimal solution for the designer. And the benefit of using that, you can compare the differences or the similarity between this design, and then you can find very interesting and share design tendency in this result. You can find they usually have a void, the horizontal void in the left-hand side of the building. And after you find this feature, you can try to understand why they have this feature. And then you can find that because there has a high-rise building on the right-hand side of the building, on this target building. So it means that most of the solar irradiation on the right-hand side of the building is blocked by this high-rise building. So if the building wants to have a very good passive cooling effect in the summer, the building needs to have focused the cell shading effect on the left-hand side of the building. So you can see that the solution provided by the EvoMass is very site and task specific. It's not just a very general solution that you should using the cell shading all around the building. You're just using the cell shading on certain part of the building. And then when you understand the implication of the in the optimization result, you can try to find some precedent and also try to abstract the design strategy and then to develop your own design concept based on this implication. And the other important thing is that because you also know that you don't need to do the cell shading all around the building, so you also informed by the optimization result that I only need to consider the cell shading features on this part of the building. So it means that the result can also provide you very specific information that how to apply this passive design strategy in your design process. So here is another example that the objective is similar. We try to optimize the solar energy potential, but I using another constraint in the EvoMass. In here I disable one of the constraint called a boundary constraint. It means that all this void can be broke the boundary of the building volume, so you can create some like a vertical courtyard in the building. So you can see that using this approach, you can see that even using the same objective for the optimization, but the result will show different tendency, and you can find that they have more vertical voids in this building. It means that the vertical void may be more efficient for the reduce the solar heating in the summer. And so when you take this optimization result, and you can also have some inspiration, or you can find some design precedents in the real world design example, and also have abstract the design strategy, and then to try to develop your own design concept in your following design process. And the last example is that I changed the design objective from the solar heat gain to the daylighting optimization. So you can find when we change the objective, the result also change, of course. And you can find another tendency here is that they usually have a void between the target building and the building on its norm, because they will try to increase the spacing between these two buildings, because the building on the north is too close to the target building, so it will block a larger amount of the daylight for the target building. So by increase the spacing between the target building and the surrounding building, you can improve the daylighting quality, or the potential, or the daylight accessibility of the target building. So after you understand the implication in this optimization result, you can also to see some very close related example in the real world, in the reality, and then also to abstract your own design scheme or the design concept to develop your own design project. So this is the basic idea of using the EvoMass when you're doing the performance-based design optimization, as well as more importantly, the design exploration. So if you come back to this diagram, you may have a better understanding of why EvoMass can support such design process. The designer can use the based on the optimization result to reformulate their design problem or reframe their design problem, and then after several rounds, several iterations of the design optimization and exploration, then they can gather a lot of the information related to the design problem, and then to develop their own design concept by combining all this information gathered from the optimization process. So here is the last slide for the lecture. So here is one very interesting sentence in a research paper about the parametric design and the optimization. The author said that they also conduct like a workshop or some experience on how designers using the computational design optimization. They find that the designer, architects, and engineering will say that the computer automate, or we say the optimization result, is often used as the starting point for the design exploration, rather than just the end of the design process. So this is basically the same idea of the EvoMass. You don't need to directly using the solution provided by the EvoMass. You're just using the EvoMass as a method to collect the information and try to find an inspiration, or to understanding the hidden the challenge or the problem of the related to the building performance. And then you can combine all this information or the knowledge and then to make up your own design idea or the design concept. So here is the end of the first 1 hour section about the lecture. So before that, before we move on to the next section, there is any question or anything you want to say about this part? Hi, everyone.
Hi.
Hi. So if a question, feel free to ask, or you want to discuss something, is also welcome. Oh, Francisco comes to our meeting room.
No question for the moment, but thank you very much for the presentation.
All right. So if we don't have any other question, I would suggest we have like maybe 10 minutes break, and we will come back 10 minutes in 10 minutes. All right. All right. See you then.
Okay.
Hi, since you are missing 2 attendees in the meeting room, so we notify them. Let me share my screen.
Yes.
All right, I just share activation code on the Slack if you can see that, and if you have a question about how to activate the using the activation code, you just here I will show you, and in the EvoMass you will find this prompt tree on the island, and then you just make one of them and click it, and ignore all the warning message, and go to the last step tab with the name information, and then to renew the activation code is all right. And the activation code there have a 2,000 trial runs, and if you are run out there, you can still apply for another 5,000 on the Football Rhino pages on the Football Rhino page, and but I guess the 2,000 is enough for this workshop. So I guess you have only 5, 7. All right, we're just missing one of them, and we are okay to start this section of the workshop. And this section is focused on is a technical section about how to use the EvoMass, and especially on the design generation part. So when you install the EvoMass on your Grasshopper, you can see this icon on this tab called EvoMass. They have a free generative component and other 4 kinds of component, but we are only cover the 2 generative component and this evolutionary algorithm component in this workshop. And the other component, the function of other component, you can still find on the some tutorial on the YouTube.
Excuse me, may I ask a question?
Yeah, please.
I just trying to use the palms sign that you mentioned, but it says that the EvoMass is expired.
Oh,
I should activate the EvoMass.
Yeah. You just activate. You should see the. Can you see the small windows pop up to ask you to type in the activation code?
Yes. Email and
So
activation.
You have you joined the Slack workspace? The Slack workspace. Here. Have you joined here?
No.
Well.
Oh, I should use this one? Okay,
Yeah, here.
Okay, great. Yes, I'll do it. Thank you.
Oh, no problem.
I got it.
Great. So let's move on. And here we will focus on cover these two generative components in this section. So we will start with the subtractive foam meshing component, this one. And if you draw one of them on your canvas, you can see there will be nothing will be generated in the grasshopper and the rhino, because before the component can generate anything or the building meshing, you need to define the parameter to generate a building, because the first thing you need to do, the algorithm or the component needs to do is what types of the building you want to generate. So you just click the setup here, and then you come to this tab, and we just go to the very simple one, just set the parameter first, and then you can get the design generated by them. So every time you change any of these parameter, you need to click the set parameter first, and then to activate the new input parameter. Otherwise, they just generate the design based on your previous parameter. And after you generate this one, and then you can use the shuffle meshing and to generate another one. But this is all based on the parameter you define in this tab. And also, if you want to take a more comprehensive or the more overview of the building generated by this parameter, you can using the sampling function. Using the sampling function, you will generate a set of design in the Rhino environment, and then you can compare when you really use that, you can see, let's say that you firstly using this combination of the parameter, and you generate like a file design, and then you can change this parameter and generate another file design, so you can make a comparison between the features related to your change of the parameter, and to decide which one is more you are more preferred to use in the optimization process. All right, this is the very basic option function here. So when you use the EvoMass, I will go through all these parameters one by one. So the first very important one is the column grid number and the floor number, which define the whole volume of the design, because when you're using the EvoMass, the first thing you need to define is what types of the building that the component will be generated. It is a high-rise tower or a middle-rise building. So the column grid number here is like a 20 by 10. So if you want to change it to make a design like a rectangle building, for example, you can change the X to 10 and set the parameter, and then you can see the building is become like a rectangle, like a cube. And if you say that this building is a high-rise tower, you can also change the floor number. Typically, you just using the same number is all right. For example, 30 and 30. And you can see that they will have become a high-rise tower. And and you are also allowed to define the minimum and the maximum of the floor floor levels, and to make the design have a little bit more design diversity in the generation part. So in that case, you can see the tower will change in their height. So so after that, you can also define the floor height of the building for the floor level. For example, here is a 4.8 meter. It is obvious too high for a high-rise tower, so you can change to like a 3.3. We usually use this number in China. And also, you can also change the column spacing of the column grid. And sorry, my keyboard has. So the building will be changed accordingly. And also you can set different value in the X and the Y direction. So in this way, you can define the basic parameter for the design, the building design you want to generate. It is a high-rise building or middle-rise building. So this is the first step when you're using the EvoMass. You need to define this column grid number and the floor number. All right, so the second thing is that you can also generate the core. The core is just like the elevation shaft, the escalator shaft, or the structural core of the high-rise building. So if you enable this, you can see they will generate a core in the middle of the building. But usually I won't use this function because firstly, they will just like here show they will have some error. And the second thing is that they will also decrease the diversity of the building because many of this void have to align with this core. So typically I will just disable it. And also the distance of generate this core is based on the fire escalation code in China, so maybe not very useful for the country other than China. And the other thing is that you can set the target gross area to control the overall volume of the design. For example, for this design, let's see how large it is. Like 15,000. So 115,000 square meters. So if we're using the gross area control, we can define how large we want the building to be. There have two options to change the to address the building to satisfy the target gross area requirement. The first one is scaling the structure. It means that they will you scale up or scale down each of this void to make the design will be very close to the target gross area you define, or you can select this one. They scaling the initial mass. It means that they will change the basic the initial volume of the whole building to make the gross area close to the target gross area you define. But in most cases, if you don't want the initial volume to be changed, you're just using this one. And so here is like 50,000, but this one is like 150,000. So let's set a quite close value here. Let's say this. So yeah, here I set a 200. Yeah, 120,000 square meters. So you can see the general design is of 140,000. So it's a little bit close than the previous one. It seems that maybe it's a little difficult to reach the target gross area if the your parameter defined here may be too difficult for the component to find the satisfying solution. So if you change a little bit, maybe or in other cases, maybe easier for the the component to find the satisfying solution. Let's see, here is the 160, maybe let's say like actually. So like this one, they can manage to find a design with a very close cross area to the target cross area you define. So this is the function for the target cross area. So we just disable them because they will usually will compute a little more time for generate the building. So they will slow down the whole design generation and the optimization process. But if when you really run the optimization, you can still activate this function. So we come back to the basic of the design generation. So after all this have been set up, you can change all this the parameter here to define the more subtle variation for the building massing generation. So we just delete this one because we need maybe the default one is more suitable to use. We generate another new component and generate the default building massing here. So in the subtractive component, you can define two types of the subtractor, which is the horizontal one, which will have a horizontal cut on the building, or the vertical one, which will create a vertical cut on the building. So if you set either 1 to 0, so it means that the building generative will only have one type of the void will be cut in the building. So here. Let's highlight the building. If we set the vertical subtractor to 0 and the horizontal subtractor to 3, you can see that all the subtractive void of the building will be on the horizontal direction, and you cannot see any of the vertical one. And well, I forgot to say the implication of these two subtractors is to generate different types of the design strategy. For example, the vertical subtractor is more like a courtyard or the atrium in the building, and the horizontal subtractor is more like a steel or the overhanging structure for the building massing. So if we reverse the number, like we set here as a 3 and here is a 0, we can find the building will only have a vertical voice in the building volume as the like as I said, the atrium or the courtyard of the building. So you can see in this case, maybe two small atrium will be merged into a large one, as I said in the previous lecture. All right, this is about the number of the subtractor, and we less to using a default number here. And all right, and in here, why did and in this 4 parameter will help you to control the size of each of these subtractor. If you are, for example, you are thinking this subtractor may be a little bit too small for your whole design, you can change this volume. Firstly, we will change the horizontal size constraint, which is this constraint will be mostly focused on the vertical one, because usually we just change the vertical one will be more related to this horizontal size. If let's say we change it to a 6 to 3, we can see that all these voids will become larger. And if you, for example, to 1 to 2, this will be a very small void in will be generated in the building massing. And go to the default. And similarly, you can also define the vertical size. The vertical size is because the vertical void will generally cover the whole building. So the vertical size constraint is usually not effective for this vertical void. But the vertical size constraint will be effective for this horizontal void to define how many floor level for each of this void will be. So if we make this a little bit larger, you can see the void will become also large. So this is depends on you, because you are the designer to define the feature of this in the generative design. For example, if this is a high-rise building, have a let's say we go back to the 30 to 30. You can find that this void may be a little bit too small, and you can also increase the this size constraint to make this void a little bit more significant, just like this. All right, so we still go back to the default number. And the other option here is the boundary constraint, which means that, as I said, that whether this vertical void can break the boundary of the whole building volume. So if we disable them, we can see that the building will be immediately break by this vertical void, and which means that the building will not keep the rectangle footprint and become like an L shape of the U shape of the as the building footprint. So this means that they can introduce more design diversity in the design generation. But just keep in mind that if you are disable this boundary constraint, they usually will create some very crazy design. For example, they will cut the building into 2 pieces. So if you don't want this happen, you will need to enable the boundary constraint. And we still keep it enable. And for this part is the facade exterior, the facade type. The facade type will mostly will be connected to the simulation software, because when you do the simulation like daylighting, the indoor daylighting, you need to define which part of the facade surface is the wall, which part is the window. So here we can make a break here, and you can see, I will come back to it later, but we just connect this to the exterior opening and the interior opening. So we can see that for the moment, the opening is quite large because we are using the glaze wall or the window wall. So if you don't want this very large window wall facade, you can change to like a straight opening. So we will see the size of the opening will also change. If you want to have more detailed opening, you can also using like the window opening here. And when you see, you can see that they will divide the building with the rectangle window, and also you can change this number to determine the density of these windows. But if you're using these facade types, you can find that they usually will cost a little bit more time for the computation, for the computing do the computation. And also you can define 2. Hello?
Can we define the window to wall ratio?
No, you can. So for a moment, there is still not very not that kind of the flexible to define everything.
Okay, thank you.
But tomorrow I will come to recently we are conducting a research that maybe cover the topic you are interested about the window to wall ratio, and all right. So, and because you're using the subtractive, you can have 2 types of the facade surface. The first one is the exterior facade, which facing the outside wall of the building, and the other type is the facade facing the courtyard or the atrium of the building. So you can define these 2 types of the facade separately. For example, you want the exterior facade will be like this type of the rectangle window, and the the courtyard using like the window wall, because maybe the courtyard have a relatively low daylight accessibility, so you can use a large window wall surface to allow more light to go into the indoor space. So when you change it, you can see that they will have two different types of the facade in the different in the facade surface based on their precision. But just keep in mind that if you're using this one, they will usually slow down the whole design generation process. So we just come back to the simple one here and delete it here first. And this is the basic of the change. So before you run the optimization, you just can play with all these parameters and to see whether the design generated by this parameter is satisfy your need. Otherwise, you can keep changing the parameter until the design generated is okay for you. So there is also some other more advanced setting for the design generation, but I typically not use it. But maybe it is good to let you know how this function. So the first function is the interfering point, which is, as I said, that we can define a point somewhere in this here and try to abstract this this void closer to the point, or expel this void away from this point. So we need to define the point in the Rhino. We cannot define it in the Grasshopper. So for example, we define a point here, and then we go back to here and to click the set point and here and set the parameter. And you can see that because we're using the positive number, so it means that the relationship between the point and the all this void is to be make it close to the attractive point. But if we're using the negative number, you can see this thing will be expelled by this point. So you can define using this function to combine some of your design intent in the design generation. For example, here maybe have a tree or have something interesting point you want have more void in this part. So to create some semi-outdoor spaces, you can use this function. So we clear it and set the parameter again. And this, you don't need to change too much. You just, this several option here is just how you to define how this horizontal void, where this horizontal void will be show up. For example, if you disable the middle floor and the roof, all the horizontal void will be generated on the bottom of the building. This kind of the design, you can use it like just like a steel building. So if you reverse it and you just only allow the horizontal void on the roof, you can have like a terrace building like this. But usually I won't use this function. I just keep all this enabled. And the other thing is the cutting boundary. The cutting boundary is but for the moment, it's not very well developed. Still need to improve in the future, but maybe just talk a little bit about it. So you can define your own, let's close here. You can define your own boundary here. And you can set the cutting boundary. And then the building will be kept within the boundary, but you can see all this edge of the building will be very jaggy because they will calculate based on the column grid. So it means that they will cut the building by using the column grid. So many users already say that this function may be not that good. So maybe in the future we change it to a more make the edge of the generated design more smooth. And we can clear the cutting boundary and go back to the basic one. And also the adding boundary, you need to use the breadth as the input. The adding the purpose of adding boundary is like, for example, if this is a complex building design, here is the podium of the high-rise tower. So if you don't, if you have a high-rise tower that is the key static, you can use this function to make the to generate the tower. So you can see that using this function, you can combine the tower and the podium of the building, and then to make all the building geometry as the input for the building simulation. Because if you are divided these two, maybe they have some overlapping part here. So using this function, these two parts can be integrated and merged into one another. And the other quite useful. This is not about the subtractive. And all right, we clear the boundary here, and also delete this. The last one is about the fixed wall. Fixed wall is more like you can customize the footprint of your building design. For example, if you want to have an L-shaped building here, you can use this fixed wall option. The starting point means the starting point from the origin of the coordinate system in the Rhino. And you can, for example, you want to have a wall here, you don't need to change here. This is 0, 0. The value of this is also based on the column grid unit. It's not the meter or the millimeter. So if 0, 0 here, it means that they will start here, and then let's say 3 and 3. So here will have a wall have a 3 column grid by 3 column grid. So this column grid this wall will be stable in the generated design. So if you say that here is the entrance of my building, so you can use this function to define your entrance. So, and also you can use this function to create a wall in the center of the building. For example, like a 5, 3, and then you can see maybe this a little bit too small. Maybe 6 to 4. So you can see there we have a fixed unchangeable wall in the middle of the building. Let's say if you already think that this is some courtyard you need to preserve, or here have a tree inside, you can use this function to cup the whole building volume and to satisfy your design intent. All right, this is all about the subtractive component. So if you have any question, you can ask now, and maybe you can also play with it. I will give you like a 3 minutes to play with it, and we will move on to the another topic of the design generation. And now you can change the number and try to see how the change of the parameter will also change the building geometry.
Sorry, I have a question about the geometry of the mass. If there's any possibility to change the angle between the edges, because I see that these are very cubes. There's any possibility to make, I don't know, different angle between the walls instead of pure volume?
You mean the wall inside the building geometry, right?
Also external. Like
sorry?
Also the external walls.
You mean the coordinate of the the design generation system? Or one thing I forget to say is here, like if you don't want this building will be like in this position, and you want to have like an angle, you can use this function like a set plane. Is that this thing you asked?
No, but I mean the wall they are orthogonal between them. But if I want more freedom in these walls, I don't want just a cube or rectangle. But I don't know.
Yeah. Unfortunately, it's impossible because it's not possible for the moment, because as I said in the previous lecture, that because using the have so many operator will compute the relationship or the position between each of the voids. So I will try to make this void more as simple as possible, because you need to align the surface of the void. So if you have like a two circle, it is more difficult to make the merge or the align operator in this scenario. And the other thing about that is that, as I said, that the EvoMass, the result in the optimization is just give you an idea or the starting point of design. So based on the information you collected from the optimization result, you can change all the geometry. You can make them like a free-form geometry as you like. But you just, because you're using EvoMass, you know, oh, here I have a courtyard. But the courtyard show in the EvoMass is just like a cube, a rectangle. You can change it to a circle and also other type of the shape. This depends on you, because the EvoMass is not to do all the thing for the designer, but just do a very small part of the thing. And the manipulation of the building geometry, I think, is still at the hand of the architects, not the computer. So
of course, I see. Thank you very much.
All right, I guess we have to move on, and we go back to here and have some other kinds of the thing in the EvoMass is that you can use this save load function that to restore all your parameters set up in this in the current component. In case sometimes you just mistakenly change some value, and then you can find the previous setting. So for example, if you are using the current parameter setter, you save it. Let's say we put it on our desktop, and just using you can type a name, and then you change some of this value. And for example, you forget your previous setup, and you can load this thing, and your parameter is all comes back. And another function of using this is that when you do the design collaboration, for example, you have a partner and you want to share your design generation or the optimization file. So you can using this way to transform or to send your design setup using this function, that you don't need to copy or send the whole GH file to your partner. So this maybe make the collaboration a little bit easier. All right, so this is the all setup for the subtractive one. So we are going to the additive one. So similarly, you open the tab here, and here is the in this part is very similar to the subtractive one, the column grid number and the floor number. So we just try to generate one of them. And let's say if you want to have a high-rise building, we must change this to 30. So so this part I won't repeat again. It is very similar to the subtractive one. The only difference is that the subtractive one, you are generate an initial volume, but for the additive one, you this parameter only define a virtual boundary in the space for all these small box to be combined or confine all these small box within this boundary. This is only different. Let's go back to 10. And in the additive component, if they have several way to also here have something like a generator call and set the target cross here, but it is very similar to the subtractive one, but I won't repeat that. And so let's start with the these two parameters. The first one is the how many small box you are allowed the component to generate. For the moment, it's a 7. So you can use this number to control the complexity of the generated geometry. For example, you think the 7 may be a little bit too complex, you can set like 4. So you can see the building will become a little bit simpler. And next to this number is the filling factor, is how much the percentage, or the basically the how much the proportion you want this building will be occupy the whole boundary. If you think this building may be a little bit too small, you can increase this number. This allow you have a global parameter to control the whole feature of the generated design. So you can see the building become a little bit fatter. And if you still think that it is too small, you can keep increase this number. Yes. So you can change this number to define the specific feature of your generated design. But there is another way to control it, is using the actual size constraint, because each of this volume will be just generally controlled by this filling factor. But if you have more specific control of each of these volume, you can using the actual size constraint. The actual size constraint means that each of the volume will be constrained by this value. For example, here is the maximum and minimum in the vertical is the 4 floor level to the 2 floor level, and the horizontal is from the 4 column grid unit to the 2 column grid unit. So if you're using this parameter, building become very small, because each one will be only have this big. So if and now they have like a 12 by 18 column grid number. So it means that if you have a more sensible building meshing, you need to increase this this number. For example, first we change the horizontal size. We can set like 10 by 5. So you can see the building will become larger, and each of them will be set within this range. And the next thing is that you can also use to increase this number to make the to enlarge the building, each of the box a little bit larger in the vertical direction. Because we have a 10 floor level, so let's say to like a 6 by 4. So you can see each of the box will be within 6 floor level to the 4 floor level. So this will make the generated design more sensible based on the spatial boundary defined by you. And similar, here have the target gross area control. Let's see how large is this one. Is like 26,000. So let's say we set like a 30,000. So the building will become larger. But typically, maybe you can see the number is very close to the target gross area you define. And the other thing about in this tab is let's close disable the boundary constraint, is that when using the additive one, when you generate a high-rise building here, for example, you set a very infeasible parameter for each of this small box. If you see that you set 30 floor level, but they only have like a 6 or to 10 floor level, you can use the full height constraint of the building. So in that case, the building will be stretched to the 30 floor level. But because this setup is not very good, so you can see they usually have no any change in the horizontal direction, vertical direction. But if you have a more feasible parameter in here, because you have a 30 floor level, let's say like a 15 by 10, we disable the full height constraint. You can see that the building will be a little bit higher. In some cases, they can have like a building like a tower. But if you want to ensure the building have a 30 floor level, you can still using this function to make the building to reach the defined floor level. All right, so the next part is the facade type is very similar to the subtractive one. So I won't repeat here, and we are going to the advanced tab. The advanced tab here you also have the interfering point. The function is all similar to the subtractive one, so you can try by yourself. And another operator here is a separation control, which means that because when I find that sorry, what sometimes you will find the building, all the small box will be stuck together. So if you want your building will be become a little bit more sparse, will be more separated from each other. So you can using this function to force all the small box to be a little bit more separate from each other. So you can define in which direction you want to separate the small box. For example, in the horizontal direction, you can see that all these things will be a little bit away from each other. And in the vertical direction, maybe not very obvious, but let's say we set this none, and you can see the building will be very close, will be more attached to each other. And if you are enable the vertical one, they will have a little bit separate from each other. And of course, you can enable both horizontal and vertical direction. To create a building more, how to say, to separate from the in the overall building geometry features. All right, this is about this part, and the fixed open floor and the open ground floor is very similar to the subtractive one about to define the which position allow the subtractor to be generated. So this is a very similar function that allow which part of the additive box will be present or generated in the spatial boundary. So so we won't go into it. And here is some track. This track, typically you just keep it default because they are usually to prevent the building to be flow in the air. So let's say if we disable all this, and you will see the building will be just flow in the air. So this is obviously not possible or not feasible to be used in the architecture design. So in most cases, you just enable all this constraint to make the building to be stand on the floor, stand on the ground. And let's see. But this function still have some possibility to be combined with the additive boundary. So the cutting boundary is similar to the subtractive one, but so I won't go to this. But in this case, we can talk about the additive boundary using the breadth. For example, here, if you disable all this and also activate the vertical thing, and also here we have a 34 level, and we change it to a little bit smaller value. For example, like 3 to 6. So we may have this kind of the box flow in the air, but if we combine it with let's see. If we can combine it with predefined building volume here, and let's pick this volume here. You can see you can generate some kinds of common to see high-rise building that have some small part will be like an overhang structure outside the building facade surface. So here is just a very trick when you're using the EvoMass to generate some kinds of the high-rise building. All right, just clear it. And the last one is the fixed wall is also the similar to the subtractive one. You can create like an L-shaped floor print for the building or some like the central courtyard in the building if you want, just like this one. So if you want to have like a very high courtyard or the atrium in the building massing using, you can use this function. But this function have their own limitation because the wall cannot be changed. So they will keep stable in the whole building geometry. So maybe this part is not the very good way to put or place atrium in this position. So if you're using this thing, usually you have a very strong functional intention in this part. For example, like you have a tree or something, you will use this function for. Otherwise, this function is not very advisable to use in the design optimization process. I guess this is the all thing about the design generation. So I will also give you like maybe we can also using this as a break. We can have a 10 minutes break, and you can have a break and also try to play with the parameter I just talked about and try to see how the how you change the parameter and also change the building geometry. And we will come back to talk about how to combine this building geometry to a building simulation component, do the massing study or the site study when we come back. So let's have a break, 10 minutes. So we will be back in 10 minutes. All right. I just share some GH file on the Slack, and I will use this GH file as an example in this section. So to set up some ties, so you don't need to establish the whole workflow step by step in here because they will be quite time consuming. So you can just download maybe the sunlight hour or the solar irradiation one to also try to use to also try to do the practice in this section. So yeah, I already posted it on the Slack. You can download it now, and also maybe give you like 1 or 2 minutes to download and open the GH file. And also there is any question about the previous section, and please you can also ask here and now.
Yes,
okay.
Actually I have one question, and probably also others will come. This is Francesco, and yeah, when I read 1 second that I get back to that file, in both this let's say generator, then the subtracting mass and the adding mass, actually there is in the setup there is column spacing parameters, so X and Y. Are these like a module that the tool used to generate the masses? So actually it means that now by default I didn't change this, the column spacing is 7.2 and 7.2 meters in my case. And this means that the sides of the building will be, let's say, yeah, a module of this 7.2, right? It can be, for example, 30 meters by 20 meters, because those are not sides that you can divide by 7.2. Is that the case?
Actually, it's not the case. Let's see whether I can draw something on here. Maybe I just open one on my previous paper to talk about this. The idea using the column the column grid unit is actually to easier for the architects to define the whole building geometry. But actually, if we just using the whole each of the column grid as the unit to generate the building, so it is basically just like a voxel approach. But actually, it is a little bit still a little bit different from the voxel approach. In fact, let's see which one. All right. Can you see this diagram on my screen? Yeah, actually, you can see here is the black dot is the column. So each of the column grid is column grid unit is like this, like a rectangle. So but so this the boundary of this subtractor or the additive mass is not to aligned to this column grid axis, but in fact between the two column they will have a divide by two different ways. Will be divided by 4 or divided by 3. So each of the surface will be find the closest boundary or this sub address or the sub axis close to them and to align with them. This is just like I want to allow. I don't allow all these surface to be move freely between the column, because usually we have like a modular thing in the architecture design. So usually we will divide the building, the column grid like a free equal distance or 4 equal distance. So I just using this idea to control to do another smaller column grid to control each of the surface of the void or the additive massive.
Okay, I think now it is more clear.
Okay, great.
Thank you.
No problem. So let's go back to the tutorial. This part we will focus on how to connect it to the building simulation, and also to conduct a very simple meshing or the site study using the EvoMass. And as you can see, if you are already open this file, the sunlight hour or the solar irradiation is quite similar. Maybe just first we're using the sunlight hour one. And the first thing you need to define is the EPW file. The EPW file is the weather data file. So here you can use this URL. I find the climate1building.org. They can you can directly using the URL to the EPW file of your location. So in that case, you don't need to, when you change your computer, you don't need to also copy, need to copy the EPW file to your new computer. So you just can open this file because they are linked to the on the internet. So maybe it is easier. But if you cannot find your you cannot use this way, you can still using this to define one existing file, the EPW file on your computer, and then to connect it to the Ladybug. But I guess most of you are quite familiar with the building simulation thing. I guess this is more a very huge challenge for you guys to do so. And the second part is that when you do this massing study or the site study, the next very important thing is you need to decide or define the context, the condition, the surrounding building. So in this example, you can here have a two breadth. The first breadth, you can define the surrounding building. So here maybe we are, because I internalize the whole geometry, so you can also pick this geometry. And let's say if we have another building, sorry. I'm not very familiar with the. Let's say we change this building on the south of our target building, and we do another to collect this thing. And yeah, we can see that the building will actually cast some shadow on our target building, but you can define the whole surrounding area based on your design project. And here will be another component is usually I will put a flat pane under the whole on the ground, because sometimes they will have some solar irradiation will be reflected by the ground and go back to the surface of the building facade. So, but I guess currently most of the simulation tool like Ladybug, they already embedded this function in the component. So this may not be very necessary in the future, but I just usually just in case they do not have this function. So usually I will put a surface on the ground, so to mimic the reflection of the solar radiation from the ground to the surface of the building. So after you define all these surrounding area, but maybe we can make a little bit larger one. Yeah, like this. Maybe also change the building a little bit. And copy another one here, and we are to collect all this surrounding building. All right. So let's say like this. And so when you connected all this thing, and the next step is just like I said that you have to define the parameter in the generation. So let's say if whether this is a high-rise building or multi-rise building, you need to define your building parameter first to create the type you want to generate. We're just doing some random change here. And after that, you can use this function to generate the let's disable the target area here, and to generate the new building massing here. And also you can, for example, here have two different. All right. So the next step is the simulation component. So the simulation component also have a important thing you need to set up. Here is the sunlight hour. So here you can define the analyze periods of your simulation here, because in China we usually focus on the winter. So I just define the December 25 as the analyzed day, and also the analyzed periods from the 7 a.m. to the 5 p.m. And you can change all this based on the climate condition of your project. For example, you are in the maybe hot climate area, so you can focus on the summer, or you can for other like a Mediterranean region, maybe you can also focus on the summer and the winter both. And all right. And after that, here is the first simulation component that focus on generate all the sunlight hour on the surface of the building. So you can also have like using a massive addition component to calculate the overall sunlight hour on the surface of the building. So like this one is like 10,000 hours of the sunlight hour in the winter solid state. So here, if we're doing the design or the meshing study, we can, because we are not involved in the optimization yet. We will talk about optimization tomorrow. So you can just using this to do a very simple meshing study to see the connection between the building geometry and the performance. If we change that, we can see the number will be decreased or increased, and also we can recall all to recall all this number to and connect it to the building geometry. And after you generate, for example, maybe 20 or 30 design solution based on this approach, you may find some tendency in this solution. For example, some kinds of the building will typically have a very higher number of the solar sunlight hour, and some kinds of the building will have maybe a smaller number of the sunlight hour. So after you generate maybe enough of the a certain number of the design, you will gradually find this tendency. This is the one thing when you're using the EvoMass, because this part is actually not necessary to use EvoMass, but because we are here in the workshop and I want to throw all the technical issue to you today. So I usually will more prefer that everyone can use this way to do some very simple random sampling design generation and try to see whether you can find some connection between the building geometry and the performance. And here is the one component that can calculate the solar hour, the sunlight hour on the surface. But in some cases, you also need to exclude the analyze from the roof, because usually you typically focus on how many sunlight hour, direct sunlight hour on the facade, because those of the sunlight can go into the indoor space, but the sunlight on the surface of the on the roof surface is actually very useless for the it's not very close connected to the indoor comfort in the winter. So in that case, you need to exclude for example, here you can disconnect the roof surface from the analyze, just focus on the facade surface. And let's come back, connect it here again. And this one is for the building itself. And here another one is focused on the surrounding building. So in this case, you can see how your building will affect the surrounding building. And similar, you can also you can connect here and put it here to see how your target building will change the sunlight hour of your surrounding building, and to try to find the connection between these two factors, because the first simulation is that how the surrounding area can affect your design, and in this part is reverse, and how your design will affect the surrounding area. And also you can here we are geometry, we are using the surrounding building. We can also replace it with this using this surface, and then to calculate how many sunlight hour on the ground, and also see this how your building can also change the shadow, the shape of the shadow on the ground. And of course, in this step, apart from you just generate some random sampling building design, you can also change some of the parameter here. For example, you can keep reduce the number here and see whether which types of the parameter here can make the design more easier to for example, to decrease the impact on the surrounding area or increase the impact on the surrounding area. So you can see the shadow, the shape of the shadow can be changed significantly when the building geometry change. So in this way, just like the, let's see. Just like this, the GIF show, you can conduct a very fast building repeat building meshing generation, and then try to see the connection between the building meshing design and their impact on the surrounding area, surrounding urban context, and which will help you maybe collect more information at the beginning of your design. So this one is about the sunlight hour. Maybe we can also take a look on the other one of the solar irradiation. Well, I guess one thing I maybe forget to say is the output of the component. Maybe I spend a little time explaining the output of the component here. Let's try to not to show the building. The output of the two components is identical. All the factor is same. Is same. So I just describe one of them. I guess is enough. The first thing is the area. The area is some numerical number of the gross area of the generative design. So like this one is like 32,000 square meter. But you can see there have a free number. I will compare later. So when you change the building, you can see the number will change. This free number is indicate the whole gross area, the floor plan area, except for the core, the geometry, the building structural core or the elevation core, and this is the gross area for the core, because we didn't generate a core, so the area for the core is 0, and the floor plan area is equals to the gross area. So if we here generate the core, you can see there will be have some number. So the core will have like a 2,000 square meters. So the other floor plan area is like 53,000 square meter. The purpose of this, because usually you will need to calculate how many floor area can be used for rent, and the floor area in the core is usually cannot be taken into account. So if you are trying to compute some economic feasibility of the design, so maybe this function may be a little bit useful. But just as I said, I never use the core function in the design generation. So because just like I said, using the EvoMass is not to find a specific solution, but just some very abstract building geometry. So using having or not having the core, I guess, will not have a very strong impacts on the result of the information extraction. So when you try to, because the area usually I will take it as a soft constraint in the optimization algorithm, optimization process. So we will come back tomorrow. So, but just to know that you cannot just directly using the value in this output, because they have free value is instead of 1. And the second one is the curve of the floor boundary. So just like this, you can see that. And I also saw some user using this function to create their own building geometry. For example, you can use like a leap. I'm not sure I can do this correct, but I try to do it correctly. Obviously I can. but you can use this function to make a very fillet on the corner of the curve if you can find a way, and then to generate building, maybe have a soft edge, soft corner of on the building geometry. This is one thing. And the floor surface here, you can see we does not use the floor surface here, but actually the floor surface is useful for some kinds of the simulation. For example, the daylighting, you need to using the horizontal surface to calculate the, for example, this comfort glaring or the accessibility of the daylight using this surface rather than using the building facade surface. And here is the roof surface. The roof surface is the one thing, because why I need to extract the roof from the floor surface is that firstly, there are some tiles have using two material of the roof and the floor surface. So if I can provide I can extract the rule, so you can easier to define the different material for these two building elements. And the second one is that I also see some application of using EvoMass. They will also take the number of the roof surface as like a function to evaluate the design. For example, I want to have a more roof tall surface. I can use this function to combine the value of the root, the area of the root surface into the optimization objective. Or I can also using this to compute how many solar irradiation can be reached to the roof of the building to calculate the potential of using like a PV panel to do the to generate some electricity for the building. So this is the purpose of why I also provide this function on the roof. And the other thing, you need to use the breadth to extract the exterior surface, and the interior surface is just the surface of the facade. But you can see there's no different, do not differentiate the wall and to the and the window on the facade. So you're using this surface to do the calculation on just like the sunlight hour or the solar irradiation. Usually just take the whole facade into the calculation. And after that is the exterior wall and the interior wall and exterior opening and interior opening. So these two can be used like when you're doing the daylighting, you need to differentiate the windows from the wall. So you can using these two output to connect it to the different component to embed different material like the glazing to the window and some panel to the wall. So you can use this to define your own material system. And the core surface and the core wall is related to the core because we do not generate the core. So this usually have nothing to be output. But in this case, they have a core, so it doesn't matter. And the last one is an interfering point. If you have an interfering point in this component, they are usually output the same point here to let you know that in this because once you set the for example, you set the interfering point in the component, the point will be restored in the whole component. So it means that when you delete the point, it doesn't matter because the point is already restored by the whole component. So this function will let you know whether you have a point or not in the component, just like this. All right, so this is about the output of the two components. So we are okay to finish that. So in this solar irradiation example, I have defined two simulation components. The one is for the winter, and another one for the summer. So you can find the winter one is from the September 1st to the February 28th. And the summer one is from the May 1st to the September 30. So this is the same evaluation function I described in the lecture. The last two examples, if you are still remember this one. We're using the summer solar irradiation to subtract the winter solar irradiation. This is the same workflow, and after that you can open it. You can see the result of the simulation. It is similar because they have some building on the maybe this is also not a very good cases. Why try to generate another surrounding building? Let's move this building to the south. Also create another one here. So you can see we are putting 3 buildings here, and some building have some influence on this part, and also have some influence on this part. And let's see, we are turning on. Let's turning on the winter one first. So this is the winter one, and maybe we'll just disable the core first. Quite annoying. So similar, you can using the shuffle the meshing to generate a set of the random sampling design and to see the connection between the surrounding building and your target building. And also here you can also to see the numerical change when you do this random sampling study. And also you can take another one here to see the, you also enable the summer one and also combine it here. We can see we have 2 values. So when we change it, we can see the 2 values change accordingly. And also you can do the subtraction here. Let the large one to be the summer and the small one to be the winter. Also connected here, so you can see the differences. So when we change the design, you can see that this difference is quite small. It's only like 2,700. So this one is a little bit bigger. So you can use this approach to generate a set of design, and also don't forget to change some parameter in here to see how we can using this approach to find the design have small differences or the large differences between the solar irradiation in the summer and the winter, and to see why this difference is large or small, and try to connect it to your to the building geometry. And also in here, you can also conduct the same simulation that how your design will affect the surrounding building. So maybe not very obvious, but you can just try to change the analyze periods on the surrounding building and see how your design will affect the surrounding building, because this is quite simple. If you have more complex surrounding, maybe a little bit more interesting to see the change of the solar irradiation. All right, I guess this is the major thing about this building simulation part. And also here I also have a example based on the view of the ladybug. You can also try this after this teaching section. And maybe I will also, if you are interested, you can also try this one based on the daylighting. But the annual daylighting is quite slow. Usually it will take you like maybe 1 or 2 minutes to finish one simulation. So I can show you here. Close this. And this is the reason I not very recommend you to use the daylighting for this stage, because the software is not that good to be combine the daylighting into the organization process. But this is basically the problem of the Ladybug. If you're using the like a Climate Studio or and is President the Diva, they are usually more effective in the compute the daylighting of the design. So you can see there is a very slow. They usually take like a 1 minute or 2 to finish the one simulation. All right, while we are waiting for the simulation to be complete, I will try to come back here to say to do a very short summary of today's section. So we have an introduction about the background of the performance-based design, performance-based building design, and also the reason why I developed the EvoMass, and also have 2 technical tutorials on the design generation and building simulation. And after this section, I would like to invite you to do a very simple massing or site analyze, just like I did in the last section. And also you can combine this with your own climate condition, and also maybe you can find a very simple project to do this kind of the analyze, and we can also maybe talk about it tomorrow, and you can present some result based on your massing study. But this is just optional, and you can decide whether to do so. Depends on your time arrangement, and so tomorrow we will focus on the design organization part, and also some case study to see the previous example of using the EvoMass in the architecture design, and the last part is to discuss to do some discussion on this based on this workshop. So we are still waiting for them, and so I guess now we can have some like a short discussion section or Q&A section if you have any question to ask. Oh, and last another thing I forgot to say, that when you're doing the massing or the site analyze, you already see the limitation of the EvoMass. They cannot generate very flexible or freeform geometry. So you try to using like a rectangle building plot for the design. All right, we finished the simulation, but they are still computing. Maybe let's, yeah, you can see the result here. Let's make this invisible first. And still have something. Oh. Where is this geometry? Anyway, you can see that this is the result of the daylighting simulation, and you can see it's very slow, and even I use a very large analyze script, but it can be still very slow. So it makes this daylighting simulation impossible to be connected to the optimization process, because usually if you are running a very short optimization, maybe cost like 2 or 3 days. So this is basically unwiseful to do so. But if you can use the Climate Studio, usually based on our current example, usually we can have maybe organization with 1,000 or 2,000 iterations within 2 or 3 days. So it is okay to use in the research purpose, but I guess is still unable to use in the practice. All right, this is it for today's workshop, and now you can turn on your camera, and if we can have a very short discussion if you want. And feel free to ask any question about, I guess maybe they're a little bit too much for 3 hours. There's too many things.
I could make one question, Francesco, again, and yeah, one is, actually I have two, but I think the second will be more appropriate tomorrow. The first is about the chords that is possible to generate. Those are generated automatically, or it is possible to control the chords also with some parameters?
Sorry, can you repeat that?
I was asking if the chords that is possible to generate.
You mean the core or the?
Yeah,
you mean the structural core?
The core into the building.
Yeah.
It is possible to control, let's say, the chords with some parameters, or they are automatically generated without the possibility to control any parameter of the core.
Yes, actually, there just have a similar question asked by one user. Said that can I create to define the distance to control the precision of the core, because for the moment the core is actually calculate the precision to the exterior surface based on the fire the evacuation distance based on the China's fire escalation core. So they say that it's not possible to change the distance based on the other countries' core. So I think it's actually not very difficult from the technical point of view, just to make the hard-coded number the value become changeable. So maybe in the next update, I will try to open this option and to let the user to input the distance value to define the precision and the number of the core generated along with the building message.
Or maybe decide the size of the core, for example, because the core could be the size. It depends how many stairs, how many vertical shafts, how many elevators, things like this.
Oh yeah, that may be a good idea, because basically mostly if you just generate maybe using one column grid unit or two, depends on the distance. Maybe if we need a larger one, maybe the user can define like this one for it needs to have a 4 or maybe 6 column grid unit to generate one core. I guess I think this is a very good idea.
Mm-hmm.
Thank you.
Okay, and then the second question, I think, as I said, is something we will see tomorrow. I noticed that the optimization component is connected, let's say, to the setup of the massing generation. So the question is it possible to select the parameters, the variables of the optimization, or they will be all used?
So you mean that whether I can externalize the parameter to generate the building massing, that using like the conventional way that using the gene pool in the Grasshopper?
No. You see, what we are seeing, can you zoom on the optimization? Yeah, I think that the genome, the variables of the optimization. So I mean, which are these? Are all the parameters used to generate the massing, or it is possible to select only few parameters, only few variables for the optimization? Okay,
I get. So it means that when you open this here, here will show you all the parameter here. So for example, let's say this component have 7 subtractor. So it means that one subtractor needs 6 parameters to define the precision and the size. So they will have like a 42 parameter. Here is have 41 because the first one is 0. It means that whether it is possible to make some of them is unchangeable by the optimization algorithm, right?
Okay, so it is possible to select the parameters in this window.
Actually, for the moment, still cannot, because I just to try to visualize the parameter, but you cannot edit the boundary. But maybe in the future, but the problem is that from the practical point of view, can you just really to change one by one, because there's a lot of work needs to be done if you setting they have like a 42 parameter and you see set each of the lower and the upper boundary. Maybe because when I develop, I try to make it can be editable, but I later think that maybe no one will be change this in using a lot of time. But do you mean to whether I can like set some of them will be set?
I was thinking maybe if there was the possibility to keep some variable, let's say, fixed, if is that the case, then change only some other variables for the optimization. But I see that actually all the variables will be used.
Yeah. Because the fundamental idea of the EvoMass is that you still need to using this variable to define each of the small box. Yeah. So if you make one of them fixed, it means that, for example, maybe one corner point to be fixed and the other corner point can be changed. I'm not sure because I never think about how we can use this function to do.
It was just a question and about how it works, but we will see also tomorrow in the optimization workflow.
All right.
Thank you very much also for the interesting presentation.
No problem. My pleasure. So any other question? Any question about today's topic or the content? Feel free to ask for now. All right. If we don't have any further question, I guess we can close call it a night and to finish today's teaching section. And if you have, you can do the massing study or the site study tonight or up before tomorrow's section. And then you have any question you can ask on the Slack. I will try to reply you as soon as possible. And all right, so still no question. So I wish you have a good day and see you tomorrow.
Thank you. See you tomorrow. Bye.
Bye-bye.